Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we have our second episode of Brian Mullins' Flat Earth Engineer. In our first episode, we talked about how planes fly from point A to point B on a rotating spherical Earth. Today we're going to finish that episode up and talk about how they go over the curve of the spherical Earth. So let's cue up the music and let Brian Mullins give his presentation.
Okay, so let's draw that. Still 2,000 miles apart, here to here. Say, this is LAX over here, JAX. Both airports are roughly at sea level. I mean, LAX is right on the water, and JAX is a little bit inland, but I mean, Florida's flat, so it's basically at sea level. So, got this curve, the Earth, on its curvature that we see over 2,000 miles. Here is our datum line, sea level. Okay, so this is LAX. This is JAX. Okay, so this distance here.
Okay, the first major problem that I see here is this. So he's got LAX over here, and then he's got JAX over here. And then he's drawing the curve of the Earth between the two. Now he's also reasoning that since LAX is on sea level, here, let's do this in a different color. Since LAX is on sea level, and Jackson is on sea level, that for some reason this is sea level, going right through the middle of the Earth. That's not sea level, that's a tunnel. Now this is sea level, comes around like this, because sea level will follow the curve of the Earth. Now why he's suggesting that sea level goes through the Earth is unclear to me. Perhaps he'll explain it as we move on.
Distance curve based on 1,000 miles an hour, 1,000 miles of distance. This is rough because where do we actually measure? Do we measure across the curve, or do we measure the distance between the 2 points? You know, miles are linear measurements, but we'll just ignore that and just keep it simple and say 1,000 miles. Now you take the curvature chart, look on here, see if you can see 1,000 miles. 1,000 miles. The height of your curve at 1,000 miles should be roughly 128.4 miles. And so this distance here is 128.
All right, so we'll go ahead and go with his 128.4 miles. I guess we'll put that right here. Now, I haven't done the math on that. He's using 8 inches per mile squared. There's going to be an error in that because that's not really correct. That's not the formula for a circle. But we'll go ahead and use 128.4. So let's go see where he's going with this.
Our plane takes off, heading this way, I guess. Has to follow the curve. It gets up to about 30,000 feet, 33,000 feet. That's 5 miles. That's, you know, a mile is 1 mile is equal to 5,280 feet. So now you're up here somewhere, and you're trying to fly over here. This, I guess. I mean, you can't fly through the Earth like that, so you still have to follow the curve, obviously. Well, this plane.
You see, this is what I'm concerned about. We have an engineer here who realizes that an airplane cannot fly through the Earth, yet doesn't understand that rote water also has to come around the curve of the Earth. This is a little bit confusing. Now, when you measure distances, by the way, on Earth, you measure it across the surface. So our measurements will be this distance right here. And as he correctly points out, the aircraft will fly a little bit above the surface, say 5 miles. So how much of a difference do you think that would actually make? Now, if you look at the radius of the Earth, all right, it's 4,000 miles. Now, the circumference of the Earth would be 2 pi times that 4,000 miles. Now, that's the distance along the surface around the Earth, okay? If you change that to the radius being 4,005 miles to take into account the altitude of the aircraft, we're going to change this to 2 pi times 4,010. Or excuse me, 4,005. That's incorrect. 4,005. Now, as you can tell, and you're welcome to do the math, that's really not going to make that much of a difference. It's basically going to be about 30 miles. So the difference between the ground track of an aircraft and its actual track at altitude going around the Earth is about 30 miles. So we're not dealing with a whole lot of anything here. Okay, I see we need to take a brief time out here and discuss the physics of aviation. All right, we've got an airplane here. Now, there are several control surfaces on this aircraft. The ailerons will be out on the wings, and what that does is that handles the roll of the aircraft in this direction. Okay? Now, this is the rudder here on top. And what that does is that controls the aircraft in this direction. See, not a roll, just a sideways bent. That's called yaw. Now, these surfaces here are called the elevators, and what that does is that controls the aircraft pitching up and down. Now, when an aircraft flies, it doesn't fly straight. It flies at a little bit of an angle of attack. Now, the reason for that is that the aircraft uses the engine to constantly climb to maintain an altitude because gravity is constantly trying to bring the aircraft down. And you can tell this that once you are stable at an altitude, using your engine to hold you up there and the pitch of the aircraft slightly positive, if the engine stops, what will happen is, one, the aircraft will not slow down, it will continue to fly at the same speed, but two, it will start to sink. All right? Now, planes do not nose down to go around the curve. They are constantly pitched up a little bit to stay at a certain altitude. And that altitude follows the curve around. So that's the way aircraft actually work. So I thought I'd clear that up real quick.
To follow this curve, the plane would constantly have to nose down. The pilot would constantly have to nose the plane down if that's how a plane flies.
Well, fortunately, that's not how a plane flies. As I mentioned earlier, the plane is constantly climbing to maintain altitude because it's fighting the pull of gravity, bringing it down towards the ground.
I thought about this. I'm like, that's crazy. The Earth is constantly curving, so it constantly has to nose down to follow it. So I got on the internet and started looking up explanations for this. People have asked this question before, obviously, and the general accepted explanation for this is that gravity does it. It's basically like it's going into orbit, and because you have that force, you have this force of gravity on the plane pulling towards the center of the Earth. It makes you follow this orbital path. It's like a ball on a string.
Okay, guys, it's not an orbital path. I guess I'm going to have to show you another quick thing here. All right, here's an aircraft. All right, and then it's got a wing, and it's got up front here It's got an engine. Now, there are basically 4 forces that act on aircraft in flight. One is thrust, and that is opposed by drag. Okay? Then we have lift, and that is opposed by gravity. Now, in order to move forward, we have to have thrust. And at a certain speed, the thrust will balance the drag at that speed. Okay? So, you increase the engine power output, you go faster, and it will reach a certain point that the speed the aircraft is being pulled forward through the air equals the amount of drag. It balances it. Now, we have a similar situation with the wings. The wings generate lift, and the lift is what keeps the aircraft up as gravity tries to pull it down. Now, just to make sure that we're very clear on what I was saying earlier, here's our aircraft and its wing, and here is the direction of flight. Now, notice the aircraft is actually nose up. Now, the reason for that is that civilian aircraft especially do not have powerful enough engines to be able to fly in absolutely level flight with the wings parallel to the ground. They have to be angled up a little bit because you have to get that extra little bit of lift. And it's going to be moving in this general direction right here, like that. So you see there's a little bit of an angle that occurs. Now, if the engine were to suddenly cut out, what will happen is the forces of gravity bringing you down will cause the aircraft to come down, but it will remain at the same angle, see? And it will remain at the same speed. It will just sink like that. So, in reality, planes are not dipping their nose to go around the curve of the Earth. What they're doing is they're constantly climbing to a set altitude above the ground, and the ground itself is curving away below them. So the altitude will also curve. It will maintain a set altitude, and that will just naturally carry it right around the curve. So that's the way aircraft actually.
So now he's got this force of gravity that's trying to make the plane follow the curvature of Earth based on the accepted explanation for what I was talking about before. So if you want to fly in a line that's tangent to a point on the Earth, then you have to fight that force of gravity that's trying to make you follow the curve. So now it's the same problem in reverse. Now you constantly have to pull up on the controls or nose the plane up, fly in a straight line. With the rudders, you're cutting through the air, but you're flying in a straight line with the rudders actually angled like this to make the plane fly straight. That doesn't make any sense. This doesn't work. That's not an explanation. Gravity is not doing this. Where's this curvature? And when you fly in a plane, you'll notice when you look out the window, the horizon, of course, looks flat, and we're told that the Earth is too big and we can't see it, and it's also at eye level. If there's really a curve, there should be a drop. This one, people argue about this one. Big argument.
Well, no, it's not an argument at all. The horizon does drop, and you can tell that from this water level right here at 9,200 feet. The level of the 2 columns of water is above the level of a lower mountain, and it's well above the horizon. And as you can see here very clearly at 5,600 feet, it's still well above the horizon. The horizon does drop from eye level, exactly as one would expect on a sphere. Well, I think before we go any further, we probably should address this, all right? Here's the curve of the Earth. like that. Okay? Now, if you have an aircraft that starts right here, this is the aircraft's altitude. Now, if it continues out on a tangent line like this, oops, didn't do that right. So if it continues out on a tangent line straight, like so, what happens to the altitude above the Earth? Notice that the altitude continues to increase. Now, if you want to look at how the aircraft is flying, let's go ahead and do it this way here. So if we draw a line directly from the center of the Earth out, notice that it is perpendicular to that aircraft. Now, if we do the same thing on this side, notice that the aircraft is actually going nose up. Same thing here, and here, and here. That aircraft is climbing. So a tangent line is not parallel to the surface of the Earth. A tangent line actually looks like this. Here is parallel to the ground. You see the angle? The aircraft is climbing.
Earth, round Earth can be, but it's becoming a huge debate on the internet. More and more people are waking up to this. It's pretty amazing. And you know what we're not taught in school is, you know, in the late 1800s there was a raging debate going on between you know, flat earthers and globalists, as they were called. You know, people still believed that the Earth was flat. Well, you know, Columbus didn't sail to America and then prove, everybody just started believing the Earth was a ball.
Well, unfortunately, you're always going to have a few people like that. You can show them all the pictures of Earth that you want, and they still won't believe it. Back in the 1800s, most people that had some education were very aware that the Earth was spherical. But there were certain religious cults that tried to make a name for themselves by saying the Earth was flat. So let's not get this confused here, Brian.
A lot of people didn't believe it, and there's actually I've read some testimonies from civil engineers in the 1800s that just say it's ridiculous, talking about laying train track and all kinds of things. So I'm at a loss here. I don't know what to think. I mean, I'm kind of thinking it's flat and stationary. I've gone to Lake Apopka, and I've taken my telescope there, and on the south end of the lake, you know, Lake Apopka is one of the biggest lakes in Florida. I think it's the second biggest. South end of the lake with my telescope sitting 3 feet above the shore, I can see the North Shore 8 miles away. Well, based on the curvature chart, there should be, what is that? Based on 8 miles, I should have a 43-foot drop from one side to the other. I shouldn't be able to see the shore. There should be a curve of water in my way. I mean, you can't see it on a rough day when the waves are in the way, but on a calm day, you can. That doesn't make sense. I should not be able to see that.
You know, Brian, I was just finishing up this video and I happened to look at this section of it, checking the sound, and I noticed that you made an error here. This is why the 8" per mile squared doesn't work. Now, this is Walter Bisson's Advanced Earth Curve Calculator. We used an observation height of 3 feet, we used standard refraction, and a distance of 8 miles. And as you can clearly see, just under 18 feet is hidden by the Earth curve. Not 40-something feet, 18. And that is well within the size of your standard issue tree. So, could you see the other shore of that lake? Of course you could. I assume that there were trees or even a house on the other side. You would see everything above about 18 feet from the lake level. Now, this is why you don't use nonsense calculations to try and find what's visible on a spherical Earth. All right, you have to use the right calculator. You have to take into account your observer height. because that 8 inches per mile squared is based on an observer height of 0, and it is the raw curvature data. But when you come up a little bit, you look down at the horizon, and as you can see that here, the dip angle is 0.027956 degrees, so it is slightly down below your eye level. You're looking down at the horizon and past it, and you're seeing everything above 18 feet or so on the foreshore. So at least use the right math. The second is you're not seeing the sand on the beach, you're seeing the trees behind the beach, and those could be 10, 20, 30 feet above the water level. So over 8 miles, it'd be pretty easy to see trees on the other shore. You know, I'd be surprised if you couldn't.
So I don't know what's going on here. You know, I've had my world turned upside down or right side up by this. I've spent a lot of time researching this. It's 7 months and seen a lot of different things. There's a lot of topics to talk about, but this is the one I thought I'd start with. So, I mean, you guys out there, you can leave comments, call me crazy if you want to, but you got to give me an explanation for this if you're going to call me crazy, and help me out here. I'd love to go back to believing that I live on a spinning ball, and this isn't some massive conspiracy, and we all haven't been duped. But human beings are very easy to fool. It's actually much easier to fool a human being than to convince a human being that they have been fooled. Coming into this world, we don't know where we come from.
You know, Brian, I think that that's a very profound statement. Human beings are very easy to fool. I think we have a really good example of that here. And it's very difficult to convince human beings that they have been fooled. Again, I think you're kind of the poster boy for that. But we're going to go through your other videos and let's have a look. Why don't we go ahead and summarize your video now? So give me a second. Okay, let's go over your two major points from this presentation. First of all, we have LAX and we have Jackson. And we have a plane going the 2,000 miles between the two. Okay? Now, your confusion was that if the Earth was rotating in that direction at 900 miles an hour, how on earth could an airplane line up on a runway going this way after taking off on a runway going that way? Okay, again, I'm very confused as to why this is confusing an engineer. Now, as we mentioned, this spot right here on the Earth is moving that way at 900 miles an hour. If your plane is parked on that spot, your plane is also moving 900 miles an hour. If it takes off from that spot, it will continue with the 900 miles an hour plus the airspeed. Meanwhile, the ground underneath it, here we'll do that. There's your 900 miles and there's your airspeed on top of it. The ground underneath it is moving at 900 miles an hour. These two right here cancel each other out and keeps you at directly over a spot on the ground. So your only vector that you're flying is the 600 miles an hour of the airplane. Likewise, even if you make a turn and go this way, all right, the spot that you are under on the ground is going that way at 900 miles an hour. Your airplane is going that way at 900 miles an hour, and your flight speed is going that way at 600 miles an hour. Okay? These two cancel each other out. Same when you line up for the airport here. The airport's moving at 900 miles an hour. You're side slipping at 900 miles an hour because you're going right over a spot on the Earth that is going eastward at 900 miles an hour. So those all cancel each other out, and you fly straight to the runway. That was problem number one. Okay, number two, you've got the arc of the Earth right here. All right. I want to know that's Los Angeles to Jackson. All right. Yes, Los Angeles is at sea level. Yes, Jackson is at sea level. This is not the datum for sea level. All right? There are people out here like Nathan Thompson, Nathan Oakley, and Anthony Riley that don't have the training or the understanding or the comprehension of earth science that you, sir, should have as a professional engineer. You know full well that datum for sea level does not go point to point like that. You know that it goes from the center of the earth out like that. So why would you put this down? All right? You know, I'm going to be honest with you, and I'm going to put this message out directly to Brian Mullins. Brian, I was contacted by some of my viewers that said I shouldn't do this series on you. All right? And I gave serious thought to it because they said that you were suffering, and some of them even raised some questions about your mental health. But the other day I turned on Globebusters. You know what they were featuring? Your videos, sir. All right? I look at people like Mind of God who quote your force the line problem. Of course, they put it out as their own, but it came from you. Now, so what I've decided to do is this. You're a professional engineer. Let's get rid of the frat boy hat and start acting like a professional engineer. You're using your engineering degree to influence people that don't know any better with this type of nonsense. So here's what I would like you to do. I want you to post a video to my channel, and I will put it up on my channel, where you repudiate this stuff. I want you to sit down and say, look, this is not the way it is. Let me show you the correct way it is as an engineer. Okay? And until you do stuff like that, I'm going to continue with all 26 of your videos, and I'm going to go through them one by one and point out your errors in comprehension and judgment when it comes to these types of physics problems, because you are influencing people on the internet that don't know any better. And you, sir, do know better. You are a professional engineer. Start acting like one. So, signing out from Northern Michigan, this is Bob the Science Guy. Thank you all for listening. Please like and subscribe to my channel. We may have some interesting videos coming up. Take care, guys.
This rabbit hole's too deep for me. Feel my brain getting real sore.